Okay, so today we're going to be talking about system design for Rexis and search. So I think the question is why system design instead of model design? Well, there's a lot of papers out there, a lot of articles out there about how to design your models for recommendations. But as you know, as the Google paper a long time ago, machine learning and the credit card interest or technical debt, machine learning is really only a small part of it. So today I want to share with you about how to design systems. But first, let's talk about why we want to design a system in this way. I think we want to distinguish between batch and real time. I think the previous speakers shared about real-time inference and real-time inference being really expensive. That's correct. So for those who are not aware, here's the difference between real-time and in the analytics form. So in batch, imagine that you have a dashboard, data points come in, and your dashboard is updated every 2 days, and you look at your nice dashboard every day in the morning. On the other hand, if we have real time, your dashboard is updated in near real time, maybe every a few seconds or so, and you get to see in real time, hey, how does the traffic change minute on minute? Does conversion rate change minute on minute? This applies to recommendations as well. In recommendations, batch recommenders, you generate it in Spark every day or so. You store it in a key value database. So given an item, you recommend a couple of other items, or given a user ID, you recommend a couple of items. So these are refreshed periodically. In real time, however, you have to generate recommendations in real time. Most of the time, these recommendations are served through an API or gRPC. So the benefit of generating it in batch is that it's all pre-computed. It's generally cheaper. You generate it once a day. You get the benefits of economies of scale, and it's simpler, right? Because your compute is decoupled from serving. So even if your computation of the recommendations fail, your serving of the recommendations is always there. And the thing is, key value stores nowadays, Redis or DynamoDB, they are very robust and scalable, with many of them providing 99.9% uptime. This greatly reduces the operational load. You just dump everything in the database and you can serve it. However, and real-time recommendations are the opposite of this. It cannot be pre-computed. Compute is the same as serving, and the operational load is fairly high. But why do we do real-time recommendations then? Well, firstly, they are useful when the customer's journey is mission-centric. For example, assuming that I'm a user on an e-commerce platform and I usually buy electronic gadgets and books, then my homepage recommendations are going to be electronic gadgets and books. But assume that right now I need a pair of hiking boots for the winter and I'm browsing on the website. Ideally, my personalized recommendations on the homepage should update to show my hiking boots with my browsing activity. In this case, batch recommendations will not update fast enough. They'll probably update tomorrow. But by then, I would have gone to another e-commerce platform or gone somewhere else to find my shoes. So we want it to be responsive. And this applies outside of e-commerce too. For YouTube, for example, the videos you watch may be different, maybe based on a different coding tutorial or something else, that or exercise video or yoga video or vacation, right? Where your next vacation booking is likely different from your last vacation booking. So it's difficult to use your past vacations, your past air tickets, or your past accommodation bookings to predict your next vacation booking. Furthermore, real-time recommendations let you serve cold start customers. So cold start customers, they are new customers, they just come on, and we don't have purchase data for them. So how do we quickly develop recommendations for them? I think there's a statistic that shows that after a person downloads the app, and 30% of users don't actually open it the second time. So what you need to do, especially if you're in a market that is rapidly expanding, you need to be able to capture your users' interest. So what this means is that if I'm a new user, I download an app, I start browsing for dresses or I start browsing for gadgets, my homepage will update immediately to meet my interests. And that keeps me sticky on the app. So we will focus on real time, aka on demand recommendation in this case. And therefore, real time recommendations need a fairly different system design as opposed to batch recommendations. Um, so, how does this system design look like? Well, let's first distinguish this between the offline and online environment. So in the offline environment, we have model training. So these are model training processes. We might build an index or build a graph, and we might load our data into feature stores. Then in the online environment, we use our artifacts that we have from the offline environment to serve our requests. And the online environment is split into two sections: candidate retrieval and ranking. So retrieval is a fast but cost approach. So what it means is fast but not precise. So it goes through millions of items to get hundreds of candidates. And we usually do this via approximate nearest neighbors or graphs. Ranking is a bit slower. In other words, it needs more latency, but it's more precise. And we can do this because we're not searching through millions of items. We only need to go through hundreds of candidates. And we can also add more features. Usually ranking is formulated as a classification problem. What's the probability of a customer buying this item, or a learning to rank problem? So now we can then put it together, right? In the offline retrieval process, we first use our training data to train an embedding model. This can be a self-supervised approach such as representation learning, or supervised approaches that predict probability of click, etc., or even building a graph. Then with this embedding model, we can embed items from the catalog and index the embeddings to allow fast lookup via approximate nearest neighbors. Then in the offline ranking step, we first build our feature store, which is we load our item and user data into efficient key value stores, for example, Redis or DynamoDB, that allow us to pick up user and item attributes and merge them before sending it to our models for prediction. We can then use these features to augment the training data for our ranking model. So the artifacts from here will be our embedding model, our approximate nearest neighbors index, our feature store, and our ranking model. Then in the online retrieval approach, when a new request comes in, be a search request or a user clicking on an item, that would be the item itself or customer itself. The new request comes in, we embed it in the same space as all our items, and then we can retrieve our top K candidates, maybe top 1,000. Then in the ranking approach, we can then add features to our candidates, adding via feature store and rank the top K candidates. So overall, this is how the overall system design looks like. Now that we understand why we want real-time recommendations and what the system design looks like, let's see how this is implemented in some industries. We start with Alibaba's example of building item embeddings for candidate retrieval. This is based on a 2018 paper. In the offline environment, session level user data are combined to build an item graph. Basically, the graph, the sequences of items that people interact with, they're used to build a graph. Now, after we have the graph, we apply a random walk on a graph. So a graph is we just random walk of 50 steps. That helps us create sequences of 50 length each. Then via their extended TensorFlow approach, they do node to vec. So essentially it's skipgram on the sequences. Then finally, with the item embeddings, they can get the nearest neighbors for each item and store into item and item to item similarity map. So over here, this is the step where they train their embedding, and you can think of this as an approximate nearest neighbors index. Then in the online environment, when a user opens the app, this goes to the Taobao personalization platform, TPP. By first, it fetches the latest items that the user has interacted with, and then based on the item to item similarity map, it retrieves a bunch of candidates, let's say 1,000. Then these 1,000 candidates are then sent to the ranking service platform, which adds all the features and performs a ranking model and returns a rank list. And this is how the users get their homepage recommendations in real time. So over here, that's the ranker. Next, let's look at how Google integrates their wide and deep learning model into production. This is from their wide and deep learning paper. In the retrieval stage, they use a combination of machine learning models and human-defined rules to get a short list of candidates. The latency requirement of this is 100 milliseconds. Then the ranking stage ranks all the items by scores. Since this step only works on a shorter list of candidates, right? They can include user features such as countries and demographics, contextual features, etc. And this has the latency requirement of 10 milliseconds. So over here, we can see here's the candidate retrieval step, here's the ranker, And over here, with the log data, they train the ranker model, which is then pushed into the wide deep learning model. So you can see it's very much similar to the approach I shared, where the top half is the retrieval step, and the right half is the offline step. Next, we also look at Facebook's embedding based approach for search. So the text here is a bit small, but I'm going to try to read out to you. So in the left side is the offline environment, right? They first train a two-tower network with a query encoder and a document encoder. So why do you need to train a two-tower network? This ensures that the query is in the same space as the document. So this outputs a cosine similarity between each query document pair. So the document embedding model of the two-tower network is then used to embed all the documents into the same space, and these are then quantized into the approximate nearest index. And with this, they train a retrieval model and a ranker model. Then in the online environment, they use the query embedding model. So remember, there's a two-tower model. The document tower is used here, and the query tower is used here. They embed the query into the same space as the documents. And then in the retrieval step, they use an approximate nearest neighbors based on their Facebook AI nearest neighbor search files to retrieve the neighbors. And then they use a feature store for their ranker. And this is how they rank the results for every search that you get. Finally, let's look at an example from DoorDash. So in the offline environment, they train models for query understanding, query expansion, and ranking. They also load their documents over here into Elasticsearch for use in retrieval, as well as attribute data into a feature store. So these attributes will be ratings for food, price points, and tags. So you can see Elasticsearch and Neo4j is the database here. So what is interesting is that in the online environment, they, instead of using approximate nearest neighbors for candidate retrieval, they use a knowledge graph instead. So the knowledge graph, based on Neo4j, expands the query by finding related tags. For example, a query for Kentucky Fried Chicken will return tags such as fried chicken and wings. So based on graph traversal, these tags are then used to retrieve similar restaurants, such as whatever fried chicken restaurant you have in your hometown. In the US, it would be Popeye and Bonchon. These candidates are then ranked based on lexical similarity and store popularity between the query and the documents. So for example, aka what's the similarity between the query itself, whatever user types in the search box, and the restaurants and food items. It also considers store popularity and possibly the search context. For example, in the morning, you're likely searching for breakfast and then breakfast type of food, and at night, you're likely searching for dinner. Finally, the rank results are then augmented with the attributes such as ratings, price points, and delivery time before being displayed to the customer. So now, this is a quick run through of various system design approaches in various companies for real-time recommendations or search. And you can see how it maps to the system design framework that I first proposed to you. Now that we've seen some examples of the overall system design, let's look at some examples of retrieval and ranking specifically. So let's start from the basics, collaborative filtering. So I guess the most commonly known approach to collaborative filtering is via matrix factorization or alternating least squares, where we have a matrix of users and items with the values of their interactions, and we learn latent features for users and items. So what I'm showing here is an alternative approach, right? All this doesn't require a matrix. We first calculate a user's weight, which is inversely proportionate to the number of interactions. What this means is that users who interact with more items tend to have more noisy behavior and they have lesser weight. Then we calculate similarity between a pair of items by summing up the weight of users who have interacted with both items and then dividing it by the product of items' weights. So essentially, what this means is that the greater overlap in user interactions, the higher item similarity. So you can see this doesn't involve any matrix factorization at all. Alibaba developed a swing algorithm, which is very similar to collaborative filtering. The key difference is the denominator here. Whereas this denominator considers the union, this denominator considers the intersection. So This makes it more selective. And here's how the swing equation might look like in simple code. Well, you don't have to read through the code right now, but rest assured, it's really just implementing the three equations here. And yes, it is in three ugly for loops. But well, in production, you probably wouldn't be doing this. But the point here is that based on these equations and code, we can see how item-to-item similarity scores can be updated incrementally in real time, right? Instead of batch matrix factorization. So this updated item-to-item similarity scores can then be used for real-time retrieval, which is how we saw Alibaba use it in their item-to-item similarity map. So we just use this similarity score, which can probably be updated every minute or so. Then let's get candidate retrieval in YouTube. Well, first they train a deep neural network, which it considers videos watched by a user, which is the watch vector, and the search queries by the user, as well as a few user demographic data. This goes through a couple of ReLUs, and the softmax is a layer that would be millions of output, and they use sampled softmax for training. Obviously, we can't do this in production. So what they do is instead they use the network to get the user vector, as well as get the video vectors, and then they put all the video vectors in the approximate nearest neighbors index. So again, once a user comes in, we pass in all the user features and all their video watchers and searchers, we get a user vector, then we apply approximate nearest neighbors. And you will see this common paradigm very often, which is embed whatever the input is, apply approximate nearest neighbors for candidate retrieval. So they use the embedding and output here. Finally, I also want to share with you about candidate retrieval and Instagram. So Instagram shared about how they created account similarity, and they adopt the word-to-vec paradigm to get account similarity. Basically, all your likes are sorted in chronological order, and we consider all the accounts from all this content. And this would be a sentence, right? So this would be the account. This would be the global context, and there's the local context. So you train this on the word-to-vec via skipgram approach, and you get account embeddings. Of course, this assumes that the content from each Instagram account is homogeneous. For example, if I'm posting about dogs, my account is a dog account. I'm not posting about dogs and gadgets and food. So that will make it very confusing to build a user embedding. Next, let's look at some examples of ranking. So here's a model that I'm sure many people are very familiar with, but oddly enough, I could never get this to work in production. So the wide and deep network, which I'm sure needs no introduction, tries to combine regular logistic regression, which memorizes the query and the item, and a deep neural network, which allows for generalization. So given a query and a target item, it predicts the probability that the user is interested in. However, you see here is that we have to iterate through all the items. So clearly, if you have 1 million food items on your on your restaurant platform, you can rank all of them. So what you have to do is that, hey, via candidate retrieval, maybe via DoorDash's approach for candidate retrieval, we get maybe the top 1,000 candidates, and then we pass it through this wide and deep learning model. And this then finally outputs the sigmoid, probably the likelihood of click or the likelihood of purchase from that restaurant. And here's the ranker from the same YouTube paper. So you can see again, they consider the series of watch videos. They are averaged and concatenated with other features, such as the user language, and then also the time since last watch, and also all the previous user impressions. So you can see we can add a lot more features here as opposed to the previous one. In candidate retrieval, the features are we have very few features because we want it to be fast. But in ranking, because we are only considering lesser candidates, we can add more features. So again, this passed through several value layers before weighted logistic regression. But the key point here is the impression video ID. This is the candidate to rank. So given 100 candidates that we can probably show to the users, which are the candidates that are most important. So that would be they train it via weighted logistic regression, which is the likelihood of watching it weighted by the total time they would spend watching it. Finally, let's look at Alibaba's behavioral sequence transformer. So recently, or really not so recently, attention has taken over in NLP. And here's how Alibaba tried to apply it in recommendations as well. So input items are represented by the item and item category embeddings. And you can see here, this is the user behavior sequence. So maybe let's say this would be the last 5 items that I've bought or the last 5 items that I purchased. Then this would be the candidate item to rank, which is the last item in the sequence. And it would predict the likelihood of the person actually purchasing this sequence, this item based on this sequence, right? And you can see, given that it's a ranking approach, we can also add a lot of other features, whereas previously in the candidate generation approach, it's very basic. It's purely based on sequences without additional metadata. So that was a lot from all the top players in the industry and with all the fancy food models. But if you are starting from scratch, trying to build a real-time recommender right now, how would you build it? Well, I highly recommend we adopt self-supervised recommendation learning, right? So Instagram does it for Instagram does it for Instagram to VAC. Uber has also done it for query to VAC. So essentially what they do is they line up all their queries based on the restaurants that people. So if you query for spicy food and Tantan noodle, you eventually purchase from Hunan noodle store. So they consider these two queries as being part of the same sentence, right? And they apply a glove-based model to learn query embeddings, where GLOVE stands for Global Vectors of Word Embeddings, which is an NLP project from Stanford. As a final example, here's how Alibaba uses user interactions. So this was the system from the system design paper that I shared earlier, where they take all the user-based sequences, combine it into the graph, where the edges between the graph is the transition probability from one item to another. Then they apply random walk to walk on a graph to create graph sequences, or you can think of it as sentences. And then they apply skipgram to learn the word-to-vec approach, to learn the embedding of each item. Then for retrieval, again, I highly recommend using approximate nearest neighbors. Exact nearest neighbors. So firstly, we're gonna convert all our items into embeddings, right? And we will find what the nearest embeddings are to assume that they will be similar to item, and we use that for retrieval. We can use exact nearest neighbors, which is cosine similarity, etc. But that's going to be too slow, and we don't really need that precision in retrieval. So approximate nearest neighbors is a good trade-off for accuracy and speed. So what's this graph that we are looking at here? There are a couple of open source nearest neighbors implementations, such as Google's scalable nearest neighbors, Facebook AI similarity search, and hierarchical navigable small world graphs. So what I did here is I ran a benchmark on these 3 algorithms. To mimic production constraints, each query only consists of a single embedding. We can also run queries in batch, but that wouldn't be similar from production environment where you only consider a single embedding at one time, unless you do binary batching, but that's a lot more complicated. So then I built and queried the approximate nearest neighbors index, tweaking several parameters, and the graph shows the trade-off between queries per second in this other latency and recall. So why recall? Because we're using approximate nearest neighbors, we're not going to get the exact nearest neighbors, so recall assesses how good this is. So what we want is to have high queries per second and high recall. So essentially the top left corner of this graph is better, and we can see over here scan, which is Google's implementation, handily outperforms the other 2 implementations, so just use scan. For our ranking model, I highly recommend you use the very simple but very difficult to beat benchmark of logistic regression. As input, we will first have user features and item features, and output will be predicting the probability of interaction, be it click or purchase or something else. I tend to start simple with a single layer, but you might want to tweak this to meet your needs. I think you don't need to go beyond 1 or 2 layers. And once you have this working well, consider adding cross features, which is simply interaction features between each user and item feature. Then to serve this, you might want to scale this to thousands of queries per second, right? Depending on the scale of your e-commerce platform or whatever platform you use. I recommend using multiple instances and a load balancer. So in the old days, how I would do this is I would put this on raw EC2 instances and set up my own load balancer and write my own traffic controller. But now with SageMaker, it makes it a lot easier, right? You just spin up, just deploy the SageMaker, tell them how many instances you want to, and you can also do auto scaling. I think Mia gave a great demo of SageMaker, gave a great breakdown of SageMaker just now and how it saves cost. I think the one thing, the other key thing that you need to know is that SageMaker is at the stage whereby your applied scientists or your data scientists can use them on their own without any engineering support. And as well as the operations and the maintenance cost is very low. So what this means is that at the point of development, you need vastly lower headcount. At the point of operational maintenance, you also need vastly lower headcount. And as we know from building machine learning systems in production, the main cost is not infrastructure costs or training costs. It is really manpower costs. So SageMaker helps you greatly reduce your manpower. Lastly, I want to share two updates that NVIDIA shared about my previous diagram. So you can see this is my previous diagram where we split it into retrieval stage and ranking stage. And retrieval is just to remind everyone, we embed the request, we get the approximate nearest neighbors index, we add features to the candidate, we get the approximate nearest neighbors, which would be our candidates. We add features to the candidates, and then we rank all of them and we show them as the results. What NVIDIA did is they further split it, which is this is the previous retrieval step. They add an additional filter step. So this filter step would exclude candidates that are not relevant. For example, if on Netflix, you might retrieve candidates that are not suitable for children or not available in the marketplace. So this will get filtered out before the costly scoring. Then in the ranking stage, this is largely similar, but they rightly pointed out that, hey, the ranking stage can be split into the scoring stage where we're scoring the candidates for each item. And then finally, there's the ordering stage. So ranking is now scoring and ordering, where ordering includes a lot of business logic. So this business logic, you'll be surprised, is highly important, but you never see in machine learning papers. For example, if I'm a Harry Potter fan and I'm looking at a Harry Potter book, it doesn't quite make sense for all my recommendations to be the entire series of Harry Potter books and the entire series of Harry Potter movies, right? It might seem very relevant from the machine learning standpoint, but it's not diverse enough. We might want to include Lord of the Rings or Hunger Games, etc. So we might include a rule that recommendations from the same series, the Harry Potter series, don't show up next to each other. So this ensures diversity in the recommendations and usually better business outcomes. So that's it. I know that was very fast. Here I am at the end of my talk. I've written quite a bit about recommendations, as well as other topics like data discovery platforms, feature stores, and how to bootstrap labels when you have none. You can find this on my site under the teardown tag. And that's the end of my talk. I welcome any questions you might have. If you want to stay updated on what I'm doing, you can find me at Twitter or LinkedIn via Eugene Yen. And of course, my site is going to be on eugeneyen.com. Once I get the video from this, I'm going to upload the video from this conference. I'm going to upload it over there as well. So that's it. All
Thank
in
you,
30
Eugene.
minutes. You're welcome.
Yeah. As Eugene mentioned, if you lovely people have some questions, please ask them. Otherwise, I have to say I love your observation about taking into account the business roles while sorting, because we get so focused on building the best model we can build, but tend to forget that we're building it for somebody, so somebody can make some decisions. So yeah, thanks for for reminding us.
Exactly. You'll be surprised how simple business rules you implement them. And these business rules, you'll never be able to access them via offline validation, right? Because the logging policy is different from the actual policy, the online policy. But once you implement them in A/B tests, you'll find that it actually generates a lot of value. But you would never know. The machine would never know that, hey, you want to balance diversity from instead of just going all out on relevancy.
Yeah, and they're a bit harder to test, right? Because you need to do an A/B test. You can't just have a metric somewhere because it doesn't work like that.
Exactly. It's almost okay. Maybe someone smarter has figured out, but I've never been able to figure out something like, hey, if I add a bit more diversity in this, if I split them up, if I change the order of the recommendations via business rule, how would the NDCG look like? So in this case, it's very difficult because all your collected data is collected via a different recommendation system, right? That recommendation system that's in production, and that's how users see it. You would never get recommendation data, and you would never be able to test how metrics would change based on your business rule, except through an A/B test, except through exporting to real users, and that's why that's slower to iterate sometimes.
Yeah, yeah. Good point. Good point. We also have some questions from the audience, so I'm gonna post one now. It's what kind of quality metrics do you use for this kind of systems?
When you say quality, what do you mean by
Um,
quality? Do you mean technical quality metrics, or do you mean recommendation quality?
I'm guessing they mean what metrics do you use to evaluate the models?
Yeah, well, in most recommendation systems, the evaluation approach is fairly standard. So I'm going to break it down into three things. There's performance evaluation, there's quality trust busters, I'll call it, and there's technical quality metrics. Performance metrics are fairly standard. We most of the time we usually consider something called hit rate, or which is just recall. You can think of it as recall. So if we show the users 10 recommendations, how many of them do they eventually click on? How many of them do they eventually purchase? That would be recall, right? Or you can consider NDCG, which is normalized NDCG, which considers ranking. The other quality metric that we have, which is very tricky uh, to assess automatically, which is the form of trust busters. So, for example, let's say I'm going to use a Netflix for example. For example, if I'm searching for Harry Potter, and all of a sudden it gives me a movie that is completely different from Harry Potter. I don't watch a lot of movies, but I think the recent movie that came out is Dune. So Harry Potter is magical and fantasy. Dune is all sci-fi, or it could be, I don't know, Matrix, Independence Day. So those would be trustbusters, right? As a customer, you might look at it and you might say, hey, that doesn't seem quite right. So all these trustbuster metrics would be you could write them as test cases. You could say that, hey, given a couple of popular movies, you get the movies recommended. What is the genre of the movie recommended? If it differs too far, you could raise a flag in your test case. And then the final quality metrics, which is your technical metrics, right? And many of previous presenters have spoken about this. I think the two main things that you want to concern yourself about is latency and throughput, right? So for example, if you are serving a recommendation system on a web page or your site would usually have some kind of latency requirements. For example, in my case, my recommendations have to be served within 80 milliseconds. Then the other quality metric is throughput, right? Maybe you can serve a model that's at 80 milliseconds, it can be highly accurate, but it cannot scale. It's only able to meet 10 queries per second. That cannot scale, right? So in my case, the throughput that I need to reach is 10K queries per second. I should be able to scale up to 10K queries per second. So beyond that, there are a couple of other technical metrics, which is maybe auto scaling, failover. Two key things that matter a lot to me as part of data, which is privacy, which is how private is your model. Does your model consume personally identifiable data? Can you deconstruct the user from your model input, as well as security, right? How secure is access to the data that you're training? How secure is your orchestration pipeline? So those are a couple of quality metrics that I consider.
Again, I have to say I love that you also you don't just highlight the raw performance of the model, but also everything else, right? Because you don't want PII leaking into the model, personally
Yeah,
identifiable information.
and if I can just recommend, if people are considering that, here's a template for machine learning system design docs that I wrote. I don't know. Oh yeah, you're not able to see it. Are you able to see it now?
Uh, no, just the
Uh,
slides.
yikes. Oh, you're not able to see it? Okay, so
With the slides.
right, here's the
So
GitHub
just
repo.
yeah, it's visible.
Yeah. So for example, in this GitHub repo, this is a template for machine learning system design docs that I use. So you have your methodology and you have your matrix. I have over here a list of technical metrics that you want to consider, again, throughput and latency, security, privacy, as well as monitoring and alarms. For example, how long does it take before you find out that you're not serving any traffic? And the final thing that I miss out is costs, which is how expensive is your model compared to the benefit of it. And this is rightly so. In fact, cost should actually be one of the top metrics that you should be considering.
Yeah, because we don't really do that until the bill comes.
Exactly.
Yeah. All right. Well, yeah, duly noted. We'll also make sure to share these links with our audience. I have to say thank you so much, Eugene. It's been a really insightful talk, and yeah, as I said, love the points that you're making. I hope to see you
Likewise.
again here in the future.
Thank you. Thank you for having me here, guys.